Okay, so we have the pleasure to have today our speaker, Dr. Alexander Plavin, who has recently graduated, I think last year, right?
Yeah.
From the Lebedev Physical Institute in Moscow. Dr. Alexander is an expert in the central parsec of active galactic nuclei, where jets are formed and accelerated. And he studies these regions from a multi-messenger perspective using photons, multi-wavelength characterization, as well as neutrinos. And today he's gonna be talking about neutrino-emitting blazars in high resolution and high energy observation. So whenever you are ready.
Yeah. Thank you for inviting me to the seminar and also for being very accommodating regarding the specific date of the seminar. And indeed, today I'm gonna give you an up-to-date details and including new results and updates on neutrino-emitting blazars, how we probe them with electromagnetic observations at the highest resolution at high energy as well. So I'll start with a brief overview of the current and recent and historical situation with neutrinos and blazars. Active galaxies and blazars, their nuclei, were long expected to be sources of high energy neutrinos long before actual observatories started working. And over the recent decades, there were lots of models, especially like both before and after the observation started to appear. So, and these models predict and explain neutrinos from blazars in very different ways. They can be produced in different regions of blazars, and still it's really not yet clear how exactly neutrinos are produced, and relevant questions of how protons are accelerated and where. And actually studying the proton production in AGN jets, proton acceleration, is one of the most important interests for studying neutrinos for astrophysics. Neutrinos are the most direct tracers of them. And the situation with protons is much less known than for electrons, and regions where they can be accelerated and interacting to produce neutrinos vary widely all over the central regions of these sources. And until recently, there was no observational evidence for that, and there was nothing to compare these models to. But recent years, well, as you definitely know, they brought lots of new exciting results regarding astrophysical neutrinos. So, and this obviously should start with IceCube results. And first, they reported the TXS of 506 source, that is a neutrino association, the first neutrino association. It's a bright blazar, pretty far away at cosmological distances from us. There was an IceCube neutrino, high energy neutrino in 2017, and also there is a Baikal paper under review. They claim that there was a neutrino in 2021 as well. And last year, IceCube reported another association. These are the only two associations reported by the IceCube. And this is also an active galaxy, but very different from the TXS of 506. It's a nearby galaxy, not really a blazar, it's just an AGN, not that highly beamed. Jet doesn't point toward us, but still it's an AGN, and a possible explanation, it's possible that these are either two independent populations of AGNs, or maybe they even have different, these sources may even have different mechanisms of neutrino production, or maybe it's not the case. Maybe they both fall into the same picture. And it's difficult to understand and form a coherent general picture studying just like one or two sources. So statistical analysis we were really like thought for, and lots of people try to find a class-based correlation, maybe like some class of blazars or sources, other sources is responsible for lots of neutrinos. And before 2021, there were lots of searches like that. They focused on correlating neutrinos with gamma ray emission, thanks to also Fermi data that was possible, and that still is possible. However, I put a few abstracts of the scientific papers before 2020, and the main result everywhere is that there is no significant correlation between gamma rays and gamma ray sources in the sky and the detected neutrinos. And this lack of gamma ray neutrino correlation remains even today, after several years have passed. In 2020, our first paper was published, and there we show that neutrinos are statistically associated with a class of radio blazars, radio bright blazars detected with VLBI. I will go into updates on this result later, but briefly, this is all the important information on this result is in these few words that neutrinos are associated from radio blazars. They come from this kind of sources. And this result was not driven by one or two sources, like there were, like depending on how you count, 10 or maybe even more of them. And after 2020, there were like lots of papers looking for, more successfully looking for blazar neutrino correlations, and other groups are also using radio or maybe some other proxies for blazars, and there were lots of works that does indicate that there is some correlation either with some electromagnetic emission or with some catalogs formed in like more involved way. Still, there were a couple of papers, like I think mostly these two, that tried to find a correlation between blazars and neutrinos, and the report that don't find any. So I should say that this statement was also remained under question, because there were seemingly contradicting results. However, I would note that they do not directly contradict, because the methodology and the samples are different between these studies, so it's not like direct contradiction, but just interpretational one. And today I'm gonna give our understanding of neutrino-blazar connection. Was it a real result or statistical fluctuation at that time? What do the three new years of data tell us? I'll attempt to characterize the typical neutrino-emitting agent, given a coherent picture of that, and briefly speculate of what we can expect in the future. So the first piece of the puzzle when trying to understand neutrino production in blazars is well, establishing associations by themselves without any more involvement. And just recently, our paper was finally accepted and published in monthly notices. And this is basically an update of our paper from 3 years ago. We utilize now it's 71 ice-cube neutrinos selected in exactly the same way as before, but taking into account the last 3 years of neutrinos, and the same catalog of 3,500 blazars detected with VLBI. It's a complete sample which nicely covers the whole sky uniformly, as you can see here with blue dots. It's a really there was lots of effort pushed into making this sample over last decade by many people in the VLBI community. And we just, again, same as 3 years ago, we want to compare whether blazars, these blazars have a stronger VLBI flux. I mean, if the radio flux is stronger for blazars around neutrino versus blazars somewhere else. If this is the case, then well, neutrinos are statistically correlated with a sample of bright blazars. I won't go into many details on the statistical procedure itself. If you're interested, you may ask me afterwards. But the result is that we do find, again, that blazars around neutrinos indeed are brighter. Their parsec scale or millisecond scale radio flux is brighter than for blazars, just random blazars in the sky. And the statistical significance of this result is 3 times 10 to the minus 4. This is the probability of a chance coincidence, so it's extremely unlikely to arise by chance. And probably even more important for us here in the current context is that compared to our paper from 2020, the p-value, well, the p-value decreases, so significance does increase. And even further, this increase in significance roughly follows the square root of n dependency in terms of sigmas. So it's very, very consistent with this being an actual result that, as expected, its significance grows with increasing number of events, as for any real correlation. So as this basically confirms, using all the current data, that our previous result was not just a temporary statistical fluctuation because it only became stronger after 3 years. We conclude again that, well, we are even more sure that this is a physical associations, and neutrinos indeed are produced in in these blazars that mostly will be bright blazars. On the right, I show you. And just for comparison, if you look at the bottom plot, the blue histogram is a distribution of radial flux for all blazars, all blazars from the complete sample, from the VLBI complete sample, and the black histogram is fluxes for blazars that fall close to neutrino detections. Clearly, there are more bright blazars. There are more blazars with these fluxes, these bright fluxes. And in the neutrino coincident set, so, well, they are indeed, this visualization of these statistical results, that they are indeed brighter. Again, I won't go into many details, but in the process, as a, well, kind of side effect, we needed to account for systematic errors of IceCube somehow, because they are definitely present. There are lots of works showing that, but it's really hard to estimate them from, let's say, first principles. So we just took a, well, let's say, trial and error approach, and these trials are counted in the p-value I showed you before, and find that under our best understanding of how IceCube reported errors are to be interpreted, this is about 0.7, 0.8 degrees systematic error should be added to them. I should know that if you heard earlier talks of myself and my colleagues, before we said that it was about 0.5 degrees, but this is not a change in our approach or methodology. It's just a change of how we understand IceCube errors are to be interpreted, and no associations themselves and no statistical conclusions change depending on that. So it's pretty robust, but for now we believe that the better estimate is 0.8 degrees. We also just barely managed to put this note into our recently accepted paper. So contact me or ask me if you need more information on why and how to reproduce it. So the statistical analysis is crucial for our understanding of the general picture, but still it's always interesting to look at individual sources and understand what makes them special. And here I highlight 3 individual associations, 3 individual blazars that are really, well, not 3 blazars, but 3 points that highlight interesting blazars. First is like my personal favorite. It's PKS 1741, shown here. It's special because it's the first doublet in the sample in neutrino sample that we select. And first it was selected as and even highlighted in the abstract of our paper 3 years ago. And a year and a half ago, there was another neutrino detection from IceCube that also is coincident with this source. So now it's the first doublet, and yeah, I was really glad to see at least one of these. Second is selected in a less systematic way, but it was also a very interesting association, also about 1.5 years ago. It's special because actually 4 IceCube detectors reported in Astro telegrams or GCMs that they detected a neutrino event coincident with this blazar. And also, I'll show you later, it also was flaring at the time. So it's a really unique case, even though most of these individual detections are not very reliable by themselves, but still it's a unique case where all four observatories made their announcement. And also I should highlight that there are two of the blazars associated with neutrinos are among the three most beamed blazars in the sky. There are only three blazars with their estimated Doppler factor above 100, and two of the neutrino-emitting ones are in the sample. So this also indicates that neutrino-emitting blazars are unusually beamed. So beaming is relativistic beaming or Doppler boosting is directly relevant in helping us to detect neutrinos as well. So to sum up the first part of my talk, the first part of the puzzle, we confirm and extend the result that neutrinos do come from blazars, specifically from radio bright blazars, and even smaller detectors such as Antares and Baikal demonstrate some hints for the correlation. Their exposition is definitely smaller than IceCube, but water versus ice seems to give them some advantage in terms of resolution. As there are still no correlation with gamma ray blazars or gamma ray sources, we conclude that radio emission is the best, it's for now the best tracer of neutrino sources, and definitely it's better than gamma rays. And just from the correlation itself, spatial associations, we can conclude that neutrino production is directly related to the jet somehow. We cannot say for now, for sure yet. And they are also beamed, and this aids the detection on Earth because they are beamed similar to photons in our direction. But clearly, even more questions remain. It's just a very rough picture for now. So let's move to the second piece of the puzzle. And this is not directional correlation in the sky, but temporal correlations. Again, there were like lots of predictions before observational data started to come in, and it was predicted that blazar flares that were long observed in electromagnetic all over electromagnetic spectrum, they are probably related to increase of injection of new emitting particles, increase of photon density. So many models predicted that neutrino production should also be enhanced, but it's still very vague without observational evidence, because flares are, it's hard to define even what a flare is, and they happen at different times at different wavelengths. So still observational studies are crucial here. And again, TXS 506 is also well known as one flaring with multi-band flare in both radio, gamma rays. Together with, coincident with the neutrino detection, it was for the IceCube event in 2017. It wasn't flaring when lower energy events came, but the Baikal paper it's currently under review and available on the archive. It's also indicates that there, like similarly to this neutrino coming at the start of this flare, there is a Baikal neutrino coming at the start of like some smaller flare. Anyway, this is a singular case again, so it's just a like hint of where to look at, because it's hard to make any conclusions with one source alone. And in 2020, 2021, there were like works, both ours and by other groups, that use samples of blazars, again selected by VLBI mostly, or other radio emission, and the result was that yes, there is a correlation observed, temporal correlation, and here basically this plot basically shows like it's kind of correlation index on the top, and on the horizon, on the vertical axis, and on the horizontal axis it's just a time delay between neutrino and radio emission. And this peak at the highest frequency we had at the time, it's just a peak around 0 delay. This means that radio emission at tens of gigahertz is enhanced at the time of neutrino arrival. These are also consistent with the result of Howard et al. And still, I should stress that compared to directional correlation in the sky, this is definitely less reliable, less significant, because it's just fundamentally more challenging to gather enough data to demonstrate a temporal correlation as analyzed in the Yanis Leodakis paper last year. So for even more reliable temporal correlation determination, we need more data, specifically more neutrinos with better resolution. However, again, I'd like to highlight a few notable individual temporal correlations. So this 0735 is the same source I shown you before, but now I also demonstrate that it was the rise of a radio flare, and it was also gamma ray flaring at the same time as all these four potentially four neutrinos arrived. Then there is PKS 1502 that has at least several papers published about it over the last few years. But well, as far as I know, originally the first paper was that we just selected it as a part of our systematic analysis in 2020 because it shown the highest individual correlate, the very highest individual correlation between radio light curve and neutrino. So this is the neutrino arrival, and this is the radio light curves. And also recently there was some preliminary result from the Antares collaboration. It was presented at ICRC, I think more than a year ago, and only now it's going to be published very soon submitted very soon to a journal, because it's large collaboration, and we need to make sure that everyone the processes are not too fast as in all large collaboration. So the official paper is only being prepared now at the final stages of it, but the result was presented at an ICRC last time. And here there is Antares flare on the top plot. There is radio flares detected by the overall telescope here, and also there is a gamma ray flare, and all in the same, basically at the same time. So it's again an individual correlations that's nice to look at, but again, this is just for visualization mostly. All fundamental results that I present are coming from statistical sample-based analysis. So what do we derive? What do we infer from neutrinos coming during the radio flares? Well, first, this means that beaming that I discussed in the previous section, it isn't the whole story. There is indeed some physical connection between radio emission, like radio photons being produced, and neutrino production. This connection may well be indirect. It doesn't mean that they are produced at the same process at the same time, at the same location. But it's indeed a physical association, but nonetheless, it cannot be just beaming. It cannot explain the temporal correlation. And together, associations with VLBI flux itself, together with the variability timescales that are roughly months or so, they unambiguously point out that neutrinos are produced in a very central parsecs, just from causality principles. These cannot be more than a few central parsecs because VLBI measures these scales, and the temporal correlation happen on the same time scales as well. Still, even given the temporal correlation, it's still not clear what's the actual connection, like the physical connection between electromagnetic photons and neutrino production. There must be some connection, but what it is, it's not clear. And where exactly neutrino production happens. Thanks to VLBI, we know very well where radio photons are produced. We have really nice images that I shown you before. They directly show parsec scales, but it's much more difficult with neutrinos. We cannot say yet. And now I'm coming to the last and the third piece of the puzzle I want to present. I should note that these are technically these are preliminary results because the paper is not yet published, but not yet submitted. But it's almost ready. We are going to submit it maybe this week in a day or two. So it's mostly finalized. Just technically, it's preliminary still. So what's the motivation to look at higher energy photons? Well, to remind you that neutrinos are useful for us mostly as tracers of ultra-relativistic protons, because they require a high energy proton for their production, but also most likely in AGN, in bright blazars, they are produced in interactions with of protons with photons, with target photons, as they are called. So then there are some pion production and pion what's called well, there's first the pion is produced, and then they turn into neutrinos that go to Earth. So our hope is or was that we can directly try to detect or not detect these target photons directly, because nothing really precludes them from reaching Earth. We just need to determine where to look for. It turns out from these plots that we need to look at X-rays. Here on the horizontal axis, I show the neutrino energy observed on Earth, and we are mostly interested in like this region, because this is where isotope sensitivity is basically the right half of the plot. And on the vertical axis are the target photons, so the energies of these photons that are also in our observers frame. And if you look at these four diagonal stripes, they all indicate the target photon dependence on neutrino energy for different different Doppler factors of the photon emission. And if the emission is a rest frame, this means that it comes from, I don't know, either some accretion disk corona or some other regions around the AGN, around the AGN core, but not from the jet. This is delta equals 1. And these are like, these stripes indicate emission coming from the jet at different Doppler factors 10, 30, and 100. So if the emission comes from the jet, then these hard X-ray observatories like ArcticCell that recently produced their first all sky catalog, or integrals that was observed for like more than 10 years, or Swift, but they, well, depending on the specifics, they may nicely fit this energy range. And if the target photons are emitted in rest frame, then we should look at lower energy X-rays at ROSAT, for example. So what do we actually see? Well, I won't go into too many details. I just say that we do see a correlation between, well, we do see that neutrino-associated blazars are really unusually bright in hard X-rays. That is those seen by ArcticCell, Swift, and Integral. And this is some visualization for ArcticCell catalog that the three sources that are well in this catalog and associated with neutrinos, they are also located at high redshift. Sorry, I somehow removed these horizontal axis. It's redshift. So we see these three associations with well, ArcticCell detected blazars. They are X-ray bright, they are distant, so it all nicely fits into well, the cosmological volume arguments to produce neutrinos. So we are pretty sure of this result, and it will probably appear on the archive on this week or next Monday. So assuming that we really see these target photons, it's still not given because it's not written on the photon if it's target the same target photon from here, or maybe it's produced in some different mechanism. But assuming that what we see are really these target photons, this means that first, the neutrinos are indeed produced in P gamma mechanism. It was, well, the most likely explanation for years already, but it's still not a like established fact. And also, this means if you look again at this energy scale, as we see correlation only with the hard X-rays and not with soft X-rays, this indicates that the target photons are produced in the jet itself. So it's not, they are not coming from the rest frame emission. If this is the case, yeah, this means that both protons are accelerated along the jet, photons are emitted in the jet, and neutrinos are also produced in the jet. So all happens in the jet, not somewhere else. And this is basically hard energy, well, high energy hard X-rays are a unique tracer of that. So now let's try putting all the puzzle together using the three pieces I just shown you. Well, as our understanding goes, the general picture of neutrinos from active galaxies as of 2023 is basically that we confirm and show that the connection with VLBI blazars remains strong and only becomes stronger when new data gets available. So this means that neutrino production is related to jets. It's beamed along the jet. So for neutrinos to be beamed along the jet, protons that participate in their production need to be accelerated along the same jet. As still there is no neutrino gamma ray association found, statistical associations found, this means that gamma rays either not produced in large quantities or they just are absorbed, they cascade down in energy, and they are not visible by Fermi. The main fact that neutrino radio temporal correlation brings us is that beaming is really not the whole story of connecting bright blazars with neutrinos. There is some physical connection. And finally, most recently, the connection between neutrino-emitting blazars and their X-ray emission indicates that, well, potentially this is the most direct physical connection between neutrinos and electromagnetic photons, because it's likely that we see, well, it's possible, it's hard to tell, but if we see really the target photons in X-rays, this means target photons come from the jet, and this is basically the unique, almost the only possible way to tell that. So I won't again go into too much detail on statistical search considerations, but as all results, all neutrino blazar connection results, both individual sources such as the XSO 506 or sample-based studies, as I shown here, they are all fundamentally statistical. The significances are not like 10 sigma yet anywhere, or like 10, 20 sigmas are far out of reach. So for statistical analysis and proper interpretation, it's crucial to get like complete or at the very least well-defined source samples. I feel that the VLBI selection specifically provides a really unique way to do that, because it provides a whole catalog of sources that covers the sky uniformly. Systematic errors of iScoop are, well, we confirm that they remain important. Some of the pretty reliable associations lie outside the originally reported iScoop errors, and there are lots of, well, there are several papers in recent years that discuss what can be done with these uncertainties, and maybe soon iScoop will really provide the systematic uncertainties as well in a uniform way, and then we can use and compare them. And just speculating for the future, if you extrapolate the growth, the significant growth from our paper in 2020 over the last 3 years, if the same rate of growth continues, we expect that the exact same analysis, if we repeat it in 5-7 years, will give us a 5 sigma significance that is kind of the nice round number that many people expect. Of course, if we use other analysis, or if some like stuff like resolution or reliability of neutrino detection improves, that will come sooner. And very short summary. So if you only remember one conclusion from my talk, I want it to be like this lines, that bright and beamed and blazars at cosmological distances are very prominent neutrino sources for teraelectron volt to petaelectron volt energies. And I won't repeat the left part because I just said it in the last slide or the slide before, but most of my talk was based on our recent paper that was just accepted to the monthly notices last week, and it has been available on archive since last November. And the future of neutrino blazar connection and these studies, it really does look bright and promising. So we are really working with most neutrino telescopes and with electromagnetic observatories to make the future come faster. Thank you. Any questions are welcome.
Thank you very much, Alexander. Very, very nice talk. I have to say that I understood, even if it's not my field, I understood most of it. So it's really good. Let's see if anyone has any questions for Alexander.
Yes, I would like to ask something. So my name is Dimitris, and I would like to ask about the target photons of the P gamma. Are they coming from the synchronous radiation from the electrons, or are they thermal photons from the disk? Or
well, it's I cannot say for sure that they come from synchrotron self-Compton radiation, but if what we see in X-rays are really target photons, they most likely do not come from the disk or around this, because the findings are not really well consistent with target photons being unbeamed. So if they come from accretion disk or its corona, then they would fall somewhere here. And what we see is a correlation with these energy ranges. So they come from the jet, but well, most likely it's in synchrotron self-Compton. What else can be there?
Okay, yes, exactly. Thank you very much.
Okay. Anyone else? I have a couple of questions if nobody wants to chime in. I want to ask you, because you show this histogram of the number of sources as a function of the BLBI 8 gigahertz flux, right? To argue that neutrinos come from, preferentially from bright blazars, right?
Yeah.
But I see that it's a flux density, it's an apparent flux, right? So is here distance playing, like the distance to the blazar, playing a role? Because you would expect this to be more, there should be a stronger association for luminous bright blazars rather than bright.
Yeah. That's both partially true and partially probably not the case. Well, of course, all else being equal, more luminous blazars, well, they produce more photons, they produce more neutrinos most likely, and they should have stronger observed fluxes. However, this is only true like all else being equal. And it turns out that both radio emission, and other electromagnetic emission, and also neutrinos, they are strongly affected by the beaming effects. So the blazars have their jets pointing, within a few degrees of our direction. And this makes them really, emit both photons and neutrinos in our direction, aiding their detection. We wouldn't see the same kind of sources at the same distances in case they were, if they were not beamed. I think if you look at this, it's the only redshift distribution I have in my presentation for now, but here you can see that, well, at least these three neutrino coincidences that are X-ray bright, they're located indeed at cosmological distances. So they must be really beamed for us to see this emission.
I see. So
actually, I think maybe I have a supplementary plot here. Yes, there is a second panel as well. It directly shows a Doppler factor, so it's a beaming effect. And again, it's only for X-ray bright associations, but these three are associated with neutrinos, and they have basically the highest Doppler factor, so they are the strongest beamed ones.
Mm-hmm. So it's, you argue that it's probably a stronger effect, the beaming factor than the.
Yeah. Both neutrinos and photons fly along the jet towards the observer.
Okay. Okay. And before Dima, I would like to ask the second question. You say that gamma ray, there is no clear association between gamma rays and neutrino sources, but I saw that you showed, I think it was in the section of temporal associations, like PKS 0239, that showed actually a gamma ray burst, right? Like
Yes.
So is that
mm-hmm.
chance, or is just like one of a kind?
Yes, the situation with gamma rays is very very difficult for now, because fundamentally, we know for a long time that radio flux is correlated with gamma ray flux, somewhat correlated, and if radio flux is correlated with neutrinos, then gamma rays also should be. However, just empirically, it turns out that this connection between gamma ray flux and the neutrino flux is weaker, if it exists. I believe it still exists, but we just cannot detect it yet. As for individual cases, there were like one or maybe even a few papers in recent years that show that maybe sometimes there is actually a dip in gamma ray curve when neutrinos are produced, and this would make sense in a single zone model, because fundamentally gamma rays are highly unlikely to escape the same region where neutrinos are produced at the same time when neutrinos are produced. So if they are produced there, then there should be a dip in the curve. And I should say that there is no single like picture of gamma ray flares or just gamma ray fluxes for all these neutrino associations.
And is this dip in gamma ray flux in any way could be associated to the excess of X-rays?
It's challenging because it's also something you can think of, because gamma rays cascade down in energies, they must cascade somewhere, but it's still not really clear how many of these gamma rays are produced, because if you see one neutrinos per source, it may be like the flux uncertainty is very large. It's maybe like 1 per 1,000 years, 1 per year, or whatever.
Okay.
Yeah, so it's challenging for now. Gamma ray is to be studied.
Okay, thank you very much. Dima?
Hi, Alexander. Thanks for the talk. I have a following question. There are many works that say that neutrinos are associated to particular subclass of blazars, either masquerading BLX or FSRQs, some subclass, let's say. When you perform this cross-correlation with radio bright blazars, have you tried to separate classes and see if the correlation increases?
Yeah, for now, it's really challenging to, if you perform one well-defined analysis, you get significance of about I don't know, 4 sigma at best that we get here. And as soon as you try to check a few other subsamples or selection criteria, you start sometimes you start getting somewhat higher correlations, but you already have so many trial factors that it's hard to tell. So for now, we just want to correlate, want to establish the correlation with a pretty well-defined class of sources. It's we only use VLBI as a proxy. It's probably the most direct proxy of just jets being pointed towards us. It's probably the best widely available observational proxy for that. And going into deeper spectral selections, it really introduces some unwanted selection effects, because for example, optical spectra or just spectral energy distributions are available for just selected subsamples of sources, and very few of them are well defined. Like it's hard to tell if you don't really understand how your sample was selected, including all observational biases. So I think it would be really important to check, but after there are even more neutrinos.
Okay, thank you.
Okay, anyone else?
Could I ask one other question? I'm sorry.
Sure.
So
Sure, go ahead.
About the processes, because we talked about proton gamma more. What about proton-proton?
Well, I know that there was a paper last year from Andrei Neronov where they discussed that maybe proton-proton is also or even more probable, but I'm not sure. The consensus seems to be that if there are bright blazars, there are way more photons there of relevant energies anyway. So if proton-protons processes go, then photon processes must go even more efficiently. That's what I understand, but yeah, this is really not not a final conclusion by any means.
Okay, thank you. Thanks.
Final questions? There's a lot of interest, I think. Okay, if not, yeah, thank you very much again, Alexander.
Yeah, thank you
for your talk. It was really interesting, and yeah, I will stop recording.